I've come up with another example to use for this next one, and this is, imagine I've done an observational study to try to figure out whether people are inflating their tires properly, and I find that at different temperatures, people fill their tires differently. The tire pressure is different, and this won't surprise those of you who've taken chemistry and know the ideal gas law, but when it's cooler out, it tends to be that people's tire pressure is lower. PV equals nRT, right? So T goes down, something on the other side has to go down, and if you're not changing volume, because the tire stays just as big, pressure goes down. So, woohoo, here we have a whole bunch of data points. I went out there on a bunch of different days and got people to stop their cars, and I measured their tire pressure while taking a look at my thermometer, and I got a whole bunch of data. Okay, so I'm going to cover a few do's and don'ts for regression here. Let's start with saying, let us say that here's the regression line, right? At the tire pressure will be, our predicted tire pressure for another car driving by is that the tire pressure will be 25.1 psi plus 0.13 for every degree Fahrenheit that it currently is outside now. I have no idea if this is accurate. Bear in mind, I know like next to nothing about actual car stuff. I just know like what it says on my car to fill my tires to, and even that I've probably forgotten. Okay, so first of all, let us say that the temperature has increased by 20 degrees over the past few hours. Does that mean that it will cause tires to be better inflated? No. Remember, these are all basically, it's hard, you can't really do this with treatments because you've got so many possible values of X really. This is more observational study, so you cannot say that an increase of temperature causes tires to be better inflated. You know, it might be the other way around, that when people inflate their tires, it makes temperatures go up. We really don't know. But the point is that we don't know causation in a scatter plot, so we cannot use any sort of causation language. If somebody gets if it gets warmer, it won't make people inflate their tires more. If it does, you know, whatever, we just see not necessarily. So we can say an increase of temperature by 20 degrees is associated with an increase of tire pressure of 2.6 psi. That you can say, but use associated with, don't use cause, no causation here. There's also the problem where you might at some point be asked if it's reasonable to make a prediction, right? You draw your least squares line and you say, aha, you can make the following prediction. If it is 50 degrees out, the average car driving by will probably have a PSI on their tires of 33. That you can do. You can make a prediction using your regression line, right? That's what the regression line is for, to help you take guesses, educated guesses, using the explanatory variable to explain away some of the random variation that there is in some of the variation that there is among points. Why are some higher than others? Why is some PSI higher than others? Because, well, it's at least partially because of temperature. R squared is the percentage of like variation that can be explained by the least squares regression line. So yeah, so you're in my example of SATs and grades, just using your typical distance from correct will be reduced by 2% in that example that I gave earlier. Okay, so in this case, sorry about the side note, I just got this panic attack that I hadn't really explained that properly in the first video. So let's say that it is really cold out. I'm in Montreal, it's the dead of winter, it's negative 40 Fahrenheit. It does get that cold like once every winter in Montreal. Probably not by the time you're watching this because of global warming, but back when I was in college, it generally reached negative 40. So now it reaches negative 38. So can I make a prediction about a point way out there? Well, if I haven't got data from way out there, if I'm not measuring things way out there, I don't know if this linear pattern is going to continue beyond this point because I haven't measured anything out there. If it drops to 0 Kelvin, I cannot use this line to predict how like inflated tires are going to be, because those are wacky situations that this doesn't account for, right? It's linear here. If I zoomed out, maybe I'd see that it's actually slightly curved. Here it looks linear, so here I can use a line, but don't go assuming things are going to continue way out there and way out there. If somebody has a GPA of 0, I should not be using my AP Stats line to predict if their GPA is 0, I should not be using that to predict their SAT scores. It will probably not also be around 1200. Maybe 1150 is my best guess for someone with a GPA of 0? No way. Just because they signed up for my AP Stats course. Like, use the data you have. Don't go beyond the X values for which you have data. If they ask you to make a prediction, that's not something you should be doing. Alright, let's talk about outliers. Outliers are going to affect the equation that's written here. Let me point this out. Not always. Outliers are really any point that stands out. So, let's say that there's this one car with, that passed by when it was 50 degrees out, and their PSI was like 60. Oh my god. Now, whenever you have an outlier, you have to check you have to suspect that there's some sort of error in your measurements. Maybe maybe your meter broke if it's way out there, or maybe this is some special exception, a car with like, I don't know, not pure nitrogen in the tires, because apparently that's a cool thing to do. So yeah, that maybe that's something you have to pay special attention to. But probably more like helium in the tires. Woo! Go floating with your car. Yeah, so that point will affect the equation a little. Sure, instead of having a least squares regression line that goes like this, if you put a point up there, it might just move the whole thing a little further up. But it won't change the equation much, because yeah, you might want to make the square of the distance from there to the regression line a little smaller, but there's so many points where the square of the residuals will get bigger as you move it up. That one point way out there probably, in general, but not always, won't affect the shape much. So that's an outlier, but not an influential point. An influential point is a sort of outlier that influences the line a lot. Imagine that none of these points are here, right? I've only bothered measuring cars when it's between 70 and 95 degrees out. So, jolly good, I have a bunch of points, and it seems to me that, let's actually erase this. It seems to me with my data, my limited data set, that that the perfect least squares line is vaguely positive. So I have a slightly positive regression line. Let me erase one more point, and another point just to make it more visibly positive. So I've got myself a jolly good, slightly negatively sloped regression line. And then I have one more measurement, way out here. Aw, damn. I was all set up with a nice pretty regression line that looked like this, with lots of small squares of residuals, distances to the regression line. Then this point came along, and it had such an enormous residual that to account for this, my line was changed drastically. Oh, that's terrible. Has to be steeper than that. This line turned out to be better. Yes, I know a lot of the residuals grew significantly, but this residual shrank so much that it accounted for it. Points that are far to the left or far to the right of the rest of the mass of points tends to have very large effects on the shape of the regression line, on the direction of the regression line. I can illustrate this even better with if I draw my points closer together, which I'll do for you now. oh look, it's a positive, slightly negative sloped regression line. And then I put one point way out here. Yeah, that's a hell of a residual. Maybe I should just do this. Yeah, a few of these residuals will grow a bit, but that one will shrink by so much, right? A point way out to the left and not in the pattern as the rest of them, or way out to the right, not in the same pattern as the rest of them, will have a lot of influence on the shape, on the direction of the least squares line. And they might ask you to comment on what would happen if another point were added, or if a point were removed, how that would, if a point were removed, how that would affect the least squares line. And that's, it won't go exactly through the point, right? Probably a little bit above it, so that those residuals will all be a little bit smaller, but you get the idea. That's an influential point because it's far to the left or far to the right, and not where you would expect the line to be just based on those other points. If the point were here, that wouldn't affect the line, it would not be an influential point. It's influential in changing the direction and location of the least squares line.